Okay, so again, piecewise function is just a function that's made up of two or more individual pieces or functions. And each of those parts has its own domain. Let's look at an example. And this is kind of really all we'll get in today. Is just start looking at one example. Okay, this is what a piecewise function looks like. Now, the minus the colored boxes, those are just there to help us keep track when we're trying to graph this thing, right? But a piecewise function, we use function notation, f of x equals, and then look, we've got this big script bracket that we put there. That's the way we indicate that this is going to be a piecewise function. Okay, inside that big tall script bracket, each row corresponds to its own separate piece of the piecewise function. So this piecewise function has three pieces. Okay, the first piece is the red piece, second piece is the blue piece, third piece is the green piece. So what about, let's take a look at just the top one for a second, right? Just the red piece of the piecewise function. Each piece comes with two parts. The first part is what we're graphing, right? That's the function that we're graphing. The red function is the function y equals 2x, just a line, right? The second part is the domain, which is telling us where that red function lives. Where is it graphed? So what does this say then? F of x is equal to 2x, so we're graphing y equals 2x whenever x is less than or equal to negative 2. Okay, so from all the way from negative infinity up to x equals negative 2, an ant would be walking on that red line. Okay, what happens at negative 2? At negative 2, we jump to the middle piece, right? The middle piece lives where x is between negative 2 and positive 4. So between negative x equals negative 2 and positive 4, now the function is the line y equals negative 1 minus x. So an ant would be walking on a different line for those x values. And then what happens when the ant finally gets up to 4? Well, he jumps onto a third piece. It's going to be the green line, y equals negative 3. Okay? Give me 1 to 5. Okay, I need everybody this is. I know we're kind of getting towards the end here, but for just a couple minutes, I want you to really focus on this. How are we doing on that? Does that make sense? What we're talking about? Okay. So the first logical thing that we might do with this then is we might want to divide this up into the regions where each of the pieces are defined, right? Where they live. You know, where would the ant be walking red? Where would he be walking on blue? Where would he be walking on green? And so we could put in these vertical dividing lines. Those aren't part of the graph. They're just there to help us organize what's going on, right? Here we've got a vertical line at x equals negative 2 because everything less than or equal to negative 2 is going to be the red region. Here we've got one at x equals 4 because between those two x values is where we're going to graph the blue line. And then to the right of x equals 4, we're going to graph the green line, right? So let's just see if we can just get through the first part. So there's our red region, right? It goes on forever to the left. We just need to graph that line in its domain. Well, to graph a line, I know we've talked about graphing lines using point slope, where we start at the y-intercept and make a slope triangle, and that's great. But here's an example where the red region does not include the y-axis, right? So we can't just start at, we're graphing the line y equals 2x plus 0, right? So the y-intercept would be 0 and the slope would be 2. But again, the y-axis isn't included in the red region, so the y-axis or the y-intercept doesn't really help us very much. What could we do instead? Well, just remember that all it takes for us to graph a line is 2 points. Any 2 points that are on the line will do. So what we could do instead is we could just make a t-table and pick x values that are convenient for us, plug those in, and find out what the corresponding y values are so we can get ordered pairs, which are just points, right? What would one x value be that would be probably the most convenient one for us to use to graph the line in the red domain? What do you think? Any ideas? Negative 2 would be great, wouldn't it? That's what you said, right? Negative 2? -2 is great because it's the boundary. We want to know where this red line stops when it gets to the boundary, don't we? So if I plug -2 in for x, what does y equal, everybody? Y would be 2 times -2, which is -4, right? Good. So we end up with one ordered pair is -2, -4. And remember that in a t-table, if we write the t-table vertically like that, the x and y values just look like an ordered pair, right? So we get one point out here, and it's going to be, is this point going to be a solid point or an open point? Does the red domain include -2 or not? It does, doesn't it? Because look, we got this equal sign right there, right? That kind of was just confusing, wasn't it? There, it includes that. Okay, so we're going to have a solid point at the location -2, -4. So I'm going to grab a solid point and come up here to -2, -4, and put a point there. Okay, now all I've got to do is pick another convenient point. How about something like just another value of x that's in the red region? Like, how about -4? If x is -4, y is -8. So I would create another point over here at -4, -8. And that's what I would get in the red region. Everybody get that? It's really not a line, it's a ray, isn't it? It starts at this point and goes forever to the left. Okay, give me 1 to 5 so far. How are we doing? Okay, all right, we'll come back to this tomorrow.